Welcome back. In part 1, we explored the life of a star. Now let's uncover the secrets of their brightness, colors, and names. Let's dive in. When we look up at the stars, one thing stands out their brightness. But how do astronomers measure this brightness? The brightness of a star is described in two ways magnitude and luminosity. Magnitude is the scale that astronomers use to measure how bright a star appears from Earth. The system was invented more than 2000 years ago by a Greek astronomer named Hipparchus. He divided stars into groups. The brightest stars were called first magnitude, the next brightest were second magnitude, and so on. Nowadays, we use two types of magnitude. Apparent magnitude tells us how bright a star looks from Earth. For example, Sirius, the brightest star in the night sky, has an apparent magnitude of minus 1.46. Absolute magnitude measures how bright a star actually is no matter how far away it is. This is the brightness we would see if star were at a distance of 10 parsecs, about 32.6 light years away from Earth. The lower the number, the brighter the star. Along with magnitude, there's also luminosity, which refers to how much energy a star produces. It's like the power of the star. Our sun's luminosity is 400 trillion watts. Stars like Alpha Centauri A are about 1.3 times more luminous than the sun. The bigger and hotter the star, the more luminous it is. Luminosity is also dependent on the star size and temperature. Stars aren't just white or yellow, they come in many different colors such as red, yellow, and blue. The color of a star is determined by its surface temperature. When we talk about the color of a star, we are really talking about the wavelength of the light it gives off. Wavelength is the length of a wave of light. Imagine the waves you see in the ocean. Some waves are big and spread out while others are small and close together. Different colors of light have different wavelengths. Red light has longer wavelength around 700 nanometers and it is produced by cooler stars. Blue light has a shorter wavelength around 400 nanometers and is emitted by hotter stars. Stars with high temperature like blue stars emit more short wavelength light, while cool stars like red stars emit longer wavelength light. This difference in wavelength helps us determine how hot a star is. The hotter the star, the shorter the wavelength of the light it produces. Even though a star might look like one color, it's actually emitting a full range of wavelengths from radio waves, low energy long wavelength, to gamma rays, high energy short wavelength. The star's color and specific wavelength of light it gives off tell astronomers what elements and compounds are inside the star. The surface temperature of a star plays a key role in determining its color and brightness. Astronomers measure temperature using the Kelvin scale, which starts at an absolute zero, the coldest temperature possible. For example, a red star might have a temperature of around 2500 Kelvin, about 2225 degrees Celsius or 4040 degrees Fahrenheit. A yellow star like the sun is around 5500 degrees Kelvin. A blue star can reach temperature between 10,000 Kelvin to 50,000 Kelvin. The hotter a star, the more energy it radiates and the brighter it appears. A star's luminosity is related to its temperature. If a star is hotter, it will shine brighter. In fact, a star's luminosity is proportional to its temperature raised to the fourth power. So if one star is twice as hot as another, it will be 16 times as luminous. Stars come in all sizes. The size of a star is usually measured in terms of how it compares to our sun. For example, Alpha Centauri A has a radius of 1.05 times the size of the sun. But stars can range from tiny neutron stars, which are just 12 miles across, to massive supergiants that are over 1000 times the size of the sun. The size of a star is important because it affects its brightness. A larger star can produce more light, so luminosity is proportional to the star's radius squared. If two stars have the same temperature but one is twice as bright, it will be 4 times as bright as the smaller star. So size really matters when it comes to stars' brightness. Stars vary greatly in mass, and this mass determines much about their life and death. The mass of a star is often compared to that of our sun, with the unit solar mass used. For instance, Alpha Centauri A has a mass of 1.08 solar masses. The mass of a star has a big impact on its surface temperature and how long it will live. Bigger stars burn their fuel much faster than smaller stars. A star with a large mass can have a much shorter lifespan because it uses up its fuel quickly. For example, a small star might live for billions of years, but a large star might only last a few million years before running out of fuel and die. Stars like our sun generate strong magnetic fields because they are made of hot, electrically charged gas. This magnetic field is responsible for features like sunspots, which are dark, cooler areas on Sun's surface, and solar flares, sudden bursts of energy from Sun's atmosphere. The magnetic field is related to how fast the star spins. Younger stars tend to have stronger magnetic fields, but as stars age, their magnetic activity often decreases. The Sun's magnetic field creates a spectacular eruption known as coronal mass ejections. They can affect Earth's atmosphere and even disturb satellite communications. When astronomers talk about the metallicity of a star, they are referring to the amount of elements heavier than helium inside the star. The universe was originally made only of hydrogen and helium, and as stars formed and died, they created heavier elements like carbon, oxygen, and iron. These elements are called metals in astronomy. Stars can be classified into different generations based on their metallicity. Population third were the very first stars in the universe and had almost no metals. Population second stars have small amount of metals and formed later in the universe's history. Population first stars like our Sun have the most metals and are named stars. The heavier metals that stars create are important because they are used to form planets including Earth and even life itself. Imagine a giant cosmic library where stars are neatly organized into categories just like books on a shelf. Stars are classified based on two things: how hot they are and how bright they shine. Astronomers use a system called the Morgan-Keenan system or MK system to do this. Let's break it down. First, stars are grouped by the surface temperature, which is like how hot the star surface is. There are 8 main categories, each representing a different range of temperatures. These categories are given letters and they range from the hottest to the coldest. O stars are the hottest and burn at extreme high temperatures. B stars are still very hot but a bit cooler than O stars. A, F, and G stars are progressively cooler, with G being where our sun fits in. K stars are cooler than the sun, and M stars are the coolest of all. There are also an L class, which includes some even cooler objects like brown dwarfs. Each of these main categories also have a number from 0 to 9 that goes with it. The number 0 represents the hottest stars in the category, while number 9 represents the coolest. So, for example, a star can be G2 or G8, where G2 is hotter than G8. Now, stars are also classified by how bright they are. This is based on how much light they give off. The brightest stars have the lowest numbers, and the dimmest stars have higher numbers. Here's how it works. First A stars are the brightest supergiants, shining with incredible power. First B stars are also supergiants, but a little less bright. Second stars are bright giants, still very bright but not as much as supergiants. Third stars are giants, which are big but not as bright. Fourth stars are subgiants, a little smaller and dimmer than giants. Fifth stars are main sequence stars, like a sun, which most stars live most of their lives in. For example, when astronomers talk about a sun, they call it a G2V or a G25. The G2 tells us that it's relatively cool and yellow star, while the V tells us that it's a main sequence star, meaning it's in the middle of its life steadily shining. So, in the MK system, stars are carefully classified by their temperature and brightness to help astronomers understand their life cycle and where they fit into the universe. It's like giving each star its own special name and number, making it easier to understand the cosmic neighborhood it belongs to. And there you have it. From their birth to their death, the life of a star is as complex as it is fascinating. Stars come in different colors, sizes, and temperatures, each one unique in its own way, lighting up the universe with their energy. Whether it's the bright blue giants or the cooler red dwarfs, these stars help us understand the incredible forces at work in our cosmos. But remember, the stars we see today are just a glimpse of what's out there, and the stories are far from over. The next time you gaze up at the night sky, take a moment to think about the incredible journey each of those stars has gone through. Who knows what new discoveries we'll make as we continue to explore the universe. Thanks for watching, and don't forget to like, share, and subscribe for more cosmic wonders. Until next time, keep looking up.